So, firstly, I would like to invite our presenter, Dr. Robbins Mathew, postdoctoral research fellow, University College, Dublin, Ireland. Today's presenter, Dr. Robin Mathew, is a research professional pursuing postdoctoral research in the area of human robot collaboration and digital twin. Dr. Robbins Mathew achieved his BTech degree from CUSAT in 2010 and MTech degree in Mechatronics Engineering from NIT Surathkal, Karnataka in 2013. He completed his PhD in Mobile Robotics from IIT Madras in 2020 and currently working as a postdoctoral research fellow at the School of Mechanical and Material Engineering, University College Dublin, Ireland. His research interests include virtual instrumentation, mobile robotics, path planning and control, and human robot collaboration. Today's webinar would enlighten us in the topic mobile robotics from path planning to control. On behalf of our college, I invite you, sir, to begin the session. Hope you all will have a wonderful session ahead. Please, sir.
Thank you, Aditi. Let me switch on my PPT. Hope you can see the presentation. Is it
Yes, sir.
Okay. Okay. So I take this opportunity to thank University College Karivatam for inviting me for this webinar, and also a very good morning to all of you, principal, vice chancellor, members of syndicate, faculties and students, and other participants. Before going to the presentation, let me introduce myself once. Robbins Mathew. I'm a postdoctoral research fellow in School of Mechanical and Materials Engineering, University College, Dublin. I completed my PhD degree from IIT Madras in 2020 in the field of control of wheel mobile robots. So I'm going to present today on some of parts which I worked on, like mobile robotics from path planning to control. So before going to the presentation, let me show you the current market trends in mobile robotics. So the market trend shows an exponential increase in both in the use and revenue from the mobile robot market. So this market include unmanned aerial vehicles, autonomous wheel vehicles, autonomous surface vehicles, and autonomous underwater vessels. I'll be concentrating more on autonomous wheel vehicles. However, the methods and other strategies which I discuss in this particular presentation will be applicable for other type of mobile robots such as unmanned aerial vehicles or surface vessels or underwater vessels. But I'll be using the images that of wheel mobile robots. So this you have to keep it in mind. So coming to the major milestones, in case of wheel mobile robots, it started, the research started in 1950s, and then when it comes to 2020, you have autonomous trucks and cars in the market. So this research started with a very small scale robot used for a different purpose, not for actually controlling the robot as such. So it was used for some other purpose in 1950s, and in 1960s, Stanford University came up with an autonomous vehicle, which is given in this figure. It's like a puller cart, which we use for moving vegetables or other things in our India. So then, in between, the major milestone in which changed the way the things worked, or mobile robot worked, is between 1970s and 1980s. When C language introduced along with sensing technologies like LIDAR and other other kind of sensors. And also, in this period only, the most popular microprocessor, H0 microcontroller and processors, H0, H5 and H05 was introduced. So this period is the actual turning period or period, pivotal period from which onwards, from where onwards, many research as well as exponential increase in the production of field mobile robots happened. So when coming to the wheel mobile robots, again it is of different type, like omnidirectional robot, where you have a robot with three wheels arranged on either side of at 120 degrees actually in the body of the robot, and these wheels are specially made. It can be moved along linearly or in straight this way, or in the lateral direction this way, using rollers which are attached to the wheels. So you by moving each wheels in particular velocity, you can actually move the robot in any direction. So by controlling individual wheels, you can control the motion of the robot. In case of synchro drive robot, you have a normal wheel which is rotatable, and then this wheel is arranged in a mechanism which can be used for turning the wheels. So by turning the wheels and rotating the wheels, you can move the robot in any direction. Then you have steerable wheel robot, where you have powered wheels, rear wheels actually. This is car-like robot. Okay, steerable wheel robots are car-like robot. You have wheels which are powered wheels, and then you have steerable wheels. By steering these wheels, you can make the robot move to in a particular direction. Then you have differential drive robot, where the motion of the robot is controlled by controlling the independent actuated wheels. So by controlling these two wheels, independently actuated wheels, you can control how the robot is moving. So the application sector of wheeled mobile robots as well as other wheeled vehicles are in healthcare, agriculture sector, consumer goods, mining, defense and security and surveillance, transportation, etc. So what is the market prediction? It shows that an exponential increase both in the revenue as well as the application. Within 3 years, the use of mobile robot will grow by 300%. We expect that the mobile robots will be available in our homes within 5 years. You may think this is I'm over predicting, but it's actually the situation here. Now we have these robots like floor cleaning robots already available in the market within a price tag of 20,000 to 30,000 rupees. Now these robots are you can purchase it, anybody can purchase it. So this price is going to reduce within 5 years and it will come around 10 to 20,000 range. Then anybody can, like a mobile, you can purchase a robot. And while I say that these robots are going to be in your homes, I mean those robots like floor cleaning robots or elderly assist robot or any other human assistance robot or like lawn moving robot. These robots will be available in the market within 5 years and it will be there in your homes as well. So coming to the relevance of these robots in current pandemic kind of situation, in this situation you have limited number of human resources available to actually in the field, in your factories and automated facility, I mean, other facility, manufacturing facilities. Especially this problem is faced by biomanufacturing sector or bioprocessing labs where you need human presence to do the experiments and develop the things. In this pandemic, they are also facing this human resource problem, or there are also other problems like the increasing the accuracy of the product from the these biomanufacturing facilities. Also, the quantity of the product has to be increased because there is a higher demand from these manufacturing facilities and production unit. So, in such scenarios, you can use autonomous robots like this to help assist the human. So you can see this robot it's developed by Franofer assisting a human to for testing the samples, taking the samples to another place, and then keeping the samples in incubation facility and moving it back to the original question and so on. This is an autonomous robot which is being there in the market, which could actually do many things autonomously. You can see how it is avoiding the obstacles and other things and then going to the required destination. So this is the relevance of robots, use of robots in manufacturing facilities and other facilities, other than the commercial consumer goods. So when you talk about autonomous wheel mobile robots or any other robot, what are the key ingredients? For me, it is path planning, obstacle avoidance, and control. If you combine all these three together in a proper way, you can make the robot autonomous. So I will explain about each of these individual topics separately. Coming to the path planning, it's the process of finding a continuous and optimized path from a given initial position and orientation to a final position and orientation avoiding the obstacle. So you have a configuration space which consists of starting point, destination point, or goal point, and obstacles kept in between. We need to find out the path from starting point to the goal point. There can be many paths like P1, P2, P3, P4, etc. However, we have to find out which is the most suitable path. So here P1 can be avoided because it is passing through the obstacle. Then you have P2 and P3, which are very bigger route or which has to move more distance than the P4. So at last, the objective is to select this P4. Somehow you have to find out the path, then you have to select which is the optimized path. Coming to the application of path planning, when we talk about path planning, always we remember the navigation of robot. There are many other applications of path planning, like here industrial robot also can use path planning for you can place operation or any other operation. You are using it actually in navigation in Google Maps. This is also used for finding how the proteins are folded in biology, like how chain of protein will fold and form a structure. Then you have autonomous vehicle lane changing problem where again path planning is used. Then you have animation in your normal animation movies and other stuffs. Then you have piano movers problem, which is a problem where a person wants to
Excuse me, we are having some technical issues. It would be sorted soon. Please stay tuned.
Hello, Aditi.
Yeah, sir.
Aditi,
Welcome
can
back. Yeah,
uh,
you can
can you,
proceed.
could you tell me where did I stop or from where the connection is lost?
Yeah, sir. Can you just play the slide?
Yeah, can you see Aditi?
Yes, sir. Yes. You can proceed, sir.
So you have other method like Voronoi diagram where you have obstacles placed over. So I'm not going to use the full screen mode here. Otherwise, I will.
Mm.
Okay, okay, okay. Hello, Aditi, can you hear me?
Yes, sir. Can you just restart the
Okay,
session from this slide?
okay. Is it visible for you?
Visibility graph and Voronio diagram is visible.
Yeah. Yeah. Whether the slides are visible for you?
Yes, sir. Slide is visible.
So, going to the Voronoi diagram, in case if there is any connection problem, please inform me. Okay.
Okay, sir. You can proceed.
Okay. So, in case of Voronoi diagram, you have obstacles in the environment, and then you have to find out a path from the starting point to the destination point. Then, what this algorithm do is it try to find out the shortest distance from two obstacles and mark the center of this line connecting these points, and then draw a line passing through perpendicular to this line. That is the line connecting the obstacles. And then similarly, it will be doing the same procedure for other obstacles as well, other combination of obstacles as well. So this obstacle will have all the neighboring obstacles and their and then mark the center and line connecting line perpendicular to those line connecting centers. And this will form a structure like this, which consists of boundaries of area which is occupied by the obstacles. And these boundaries will be considered as a connected graph. And then these connected graph will be used by a graph searching method to find the optimal path from starting point to the destination point. So you can have a path like this or like this and many other combination. So path graph searching algorithm will select the best path. Then you have cell decomposition method where this configuration space has an x coordinate and y coordinate, and we will divide this configuration space either vertically or horizontally based on the obstacle. So the vertices of the obstacle or nodes of the obstacle will be used for dividing the space. So each node or each vertices of the obstacle will divide the space into two, like left hand side and right hand side. In this case, I divided the space in vertical way. So here in left and right, again this vertex again will through this vertex we will draw a line which is parallel to the y-axis. This is an imaginary line which is drawn, and then the upper half of this line will be divided equally, like using this point, which is considered as another node. Similarly, lower half in this node, and here in this case of this vertex, this is the one half, and the other half you have obstacle portion over here. So from here it is considered, and this is the center. Then after marking all these, you will get a graph like this, which is divided into different sections, and then nodes placed uh, along each section, and then center of each section is also marked. Then these nodes are then connected to get a graph. So you have graph like this, etc. You have path like this and like this. From this, I will select the best path. This is considered as the best path. Then you have probabilistic roadmap method, which is a sampling based method. Here you will put a you have to go from starting point to destination point again. You have many obstacles, one, two, three, and this configuration inside the configuration space will place random nodes. The criteria here is it shouldn't the random node shouldn't fall under any obstacle, space occupied by the obstacle. Once you place the random nodes, you connect all the random nodes with all other random nodes. So again, the connection shouldn't pass through any obstacle. Once this connection is made, you have a connected graph. And from this connected graph, you will find out which is the best suitable path or optimized path using graph searching algorithm. Then you have rapidly exploring random tree method where we have to go from the starting point to the destination point, avoiding this obstacle. And here, what we do is we'll first generate a random node uh, at the configuration space at some place, only a single random node, and try to connect this random node with the initial point. Then, if its distance is too far, uh, at a distance predetermined by the user, another node will be marked. And the direction of this node will be towards the direction of the line connecting the node 1 and node 2. Then, then this will be connected, and then next node will be selected randomly, and it will be connected to the nearby available node. In this way, the process continues. Again, this connection shouldn't pass through the obstacle. And once this process is continued over many steps, you will get a path from starting point to the destination point. When you think logically, you will think that it will take much time to get a possible path from starting point to the destination point. But actually, it is not the case. It is a very fast algorithm, and these two algorithms, rapidly exploring random trees and probabilistic roadmap method, are one of the most used algorithm in path planning and in real-time programs. And this then find out the path, possible path in a much faster way. This is called randomly exploring random trees because the connection made looks like a twigs or structure of a tree. That's why it is called as rapidly exploring random trees. Then you have artificial potential field method where you have starting point and destination point and obstacle kept in between. The starting point as well as the obstacle is considered to generate a repelling field. It's an imaginary field, and then destination point is assumed to have a uh, uh, another field generated, which is attracting field, and then you have field lines all over the configuration space. And the robot will take a particular path which is having the highest delta change of this particular field. Okay, like from here to here. And when it reaches here, the repelling field will act and it will move away from the obstacle. This can be considered as water flowing from a hilly place to downstream. Then once you have the connected graph, which is like this from visibility graph, use some kind of graph searching technique to find the shortest path. How to find out the best route? First, you have to give assign a weightage to all the connected lines. So from here onwards, uh, till whatever the connected lines are there, you give assign some weightage. This weightage is based on the distance between the nodes as well as the time it takes and many other parameters. These parameters can be determined by the user. So this weightage is a function of many parameters. It's not only the distance between these two nodes. Once you put the weightage all over this graph, you can find out which is the path which is having lowest total weightage. So then ask the robot to move through this path. For finding which is the path having lowest weightage, we can use many algorithms like Dijkstra search algorithm, SR algorithm, V-star algorithm, or any angle path planning algorithm. There are many other algorithms. This A-star and V-star. Okay, 1 minute.
Hello, sir. You can
Yeah.
continue.
Yeah, okay, okay. I thought something happened in between. Okay.
No, sir.
So, okay. So again, this SR and DSR itself is a vast field. There are many other algorithms developed from this, and you can find these algorithms in literatures. And I'm not going to explain all these algorithms today because it takes much more time. Coming to the obstacle avoidance, I'm just showing a video where I'm trying to avoid an obstacle. It's just moving away from the obstacle and trying to avoid it. So by obstacle avoidance, we doesn't mean this scenario where it just avoids the obstacle. By obstacle avoidance, we mean it has to avoid the obstacle as well as it has to find a route to the destination point. Okay, this is just obstacle avoidance, avoiding the obstacle only. It's not the actual obstacle avoidance which we need. So for scientifically finding the or avoiding the obstacle, you have many other methods like the vector field histogram method, where you have the robot which is moving, and then you have obstacle here. While it moves, it detects an obstacle using lidar or sonars, and then it will find out what is the probability of having an obstacle at a particular position based on this lidar data. Once you have this probability graph, you will use this graph and place it over this particular uh, graph where I mean x-axis is the direction of travel and y-axis is the amplitude or probability of getting an obstacle. So this x-axis represent the direction from the center of the robot when it turns with respect to the robot, how the obstacles are arranged and what is the probability of finding the obstacle. So this graph will be made from the sensor data. From this graph, the robot can identify which at what direction it has a gap. So probably the robot will have a gap here or another gap here, and it has to decide through which gap it has to go. So either it can go through this gap. It depends on where the destination is. So vector field histogram method uses this particular graph to find the gap in the configuration space and move through the gap. Then you have nearness diagram, where again the robot will detect all the obstacle around its space using lidars or sonars. And once it detects the obstacle, it will find out how the obstacles are arranged. If suppose you have multiple obstacles, you will arrange those obstacles in a graph. Then the robot is going to put these obstacles, the way it is arranged, into different uh, classes like LS1, LS2, HSW or HSNR. And then based on this classification, it will find out whether it is safe to move fast, slow, or with an angle. It will determine. So based on this, in which way the obstacles are arranged, robot will take a decision. So again, this decision also depends on the destination point. It's not only the how the obstacles are arranged; it also depends on the destination. Then you have bug algorithm. There are many more algorithms which are part of bug algorithm. I just showed here bug zero, bug one, and bug two. In case of bug zero, it's a common sense algorithm. You have obstacle of the space, and you have robot going from starting to destination point. And when first turns towards the destination point and moves straight, and when it detects an obstacle, it tries to circumnavigate. And while circumnavigating, it will check whether there is a possible path, free path to the destination point. If there is no path, then it continues unless it reaches here where it finds a possible path which is not occupied. Then it will move straight, and this process will repeat on the second obstacle until it reaches the destination point. But although when we think in a common sense, we think that this is the correct algorithm, it is the optimized algorithm to go to the destination. But in many cases, this fails when obstacles comes in particular configuration or particular way. This algorithm fails. So solve this problem. We have bug one algorithm where the robot goes up to here. When it detects obstacle, it circumnavigate the obstacle fully. While circumnavigating, it will find out what is the shortest distance to the destination and what is the point from where the destination is at the shortest distance. Then it will store this particular location and continue circumnavigation till it reaches the initial starting point of the circumnavigation. Once it reaches the starting point of circumnavigation, it will find out which is the shortest path to the shortest distance point, which is this point. And use that path back to the shortest distance point, and then from here it will go back to the destination point. If another obstacle is detected, this process is repeated again. And again, in all these cases, the direction of circumnavigation, whether it is in clockwise or anti-clockwise, it is determined by the user, uh, predetermined by the user actually. Then you have Bug2 algorithm where the robot again circumnavigate, it won't circumnavigate completely. Once while circumnavigating, it reaches a point where the line connecting starting point and destination point will pass through. It will stop circumnavigating and take this path towards the destination point. And this process repeats until the robot reaches the destination point. Till now, I talked about avoiding the obstacles which are static in nature. Now you have collision avoidance where the obstacles are also moving. Then you have many other methods like dynamic window approach, collision cone approach for solving this kind of problem for avoiding the dynamic obstacles. So in case of dynamic window approach, you have robot here and obstacle here which is also moving. And then based on the motion of the obstacle as well as the motion of the robot, we will create a map which is y-axis is velocity, linear velocity of the robot, and sorry, y-axis is angular velocity of the robot, and x-axis is the linear velocity of the robot. And then we'll find out what are the velocities at which the robot can move without hitting the obstacle. So this is the space under which inside if a point comes at that point, the robot, if you take the velocity at that point, the robot won't hit the obstacle. So uh, from here you can understand if the robot moves backward, it's not going to hit the obstacle. Similarly, if it turns at a higher rate than the linear velocity, well, it is not going to hit the obstacle. It will turn away and go back. So this is the graph. From this, a point will be selected for controlling the robot. Then in case of collision cone approach, you have robot moving in this direction and obstacle moving in this direction. And it will find out the point at which this collision happen when you move these two at a particular velocity in particular direction. Again, for finding this collision point, we will consider the size of the obstacle as well as robot. So this is the area where the collision can happen. Once you know the area where the collision can happen, we can find out what is the angle at which this collision can happen from the initial point. Then you can also find out what is the velocity at which the robot has to move to avoid the collision. So by selecting the velocity of the robot and the angle at which it has to move, this collision can be avoided. This is an obstacle avoidance scenario, video of an obstacle avoidance scenario. Use back to algorithm, again, robot going along, circumnavigating and going to the destination point. This we did in the lab. For obstacle avoidance or obstacle detection, we have many technologies like LIDAR, light detection and ranging. This is a LIDAR sensor. From LIDAR data, you can create a map. Similarly, sonar, sound navigation and ranging. So you have sensors like these, infrared LEDs and vision-based sensing method. So this can be mono or zero type sensors based on the situation. Coming to the control, so you have this graph or path which is planned by the robot. This can be obtained from earlier path planning technique, this graph. And then we have obstacle here and the robot here. This has to go to the destination or go to. When you have, when I explained earlier about this graph, these graphs are having nodes and line connecting them. So this is that kind of graph. This dotted line is that kind of graph. But in many cases, the robot cannot directly use this kind of graph to go from the starting point to the destination point. In such scenarios, first a path smoothing algorithm will be utilized to smoothen this path and make a smooth path like this, and then the robot will be controlled through this path, smoothen path instead of going directly to this dotted path. So for controlling the robot, in case of this robot, this is a differential drive robot, which is kept in a configuration space. You have XI initial axis, YA, XI and YA as initial axes, and robot has linear velocity and angular velocity. So a control law should select a particular linear and angular velocity to make the robot go through this selected path or the smoothened path. So the purpose of the controller is to select these control velocities. Once this control velocity is obtained, it will be again this function will be used to convert the control velocity to the linear and angular velocities of the individual wheels, and then the controller will come into effect. So hence the need of the controller is for selecting this VI and omega I. For this purpose, you can use open loop controller. Here you have a robot here which has to go through this rectangular path having length L and width P. And there is a stylus kept behind the robot who trace the path tracked by the robot. And this is again a differential drive robot. You have this control equation over here which controls the motion of this robot. And for open loop control, what we do is move forward for B by VI seconds, keeping omega 1i equal to omega 2i. This means it will move straight forward for B by VI second. VI is determined by the operator, and omega is also determined by the operator. Then once it reaches here, turn. Just take a turn. So for turning, you have to keep omega 1i equal to minus omega 2i, and then turn for theta by omega I second to make this turn. So if here it is theta equal to 90 degree, it will make it a 90-degree turn, and this process will continue till it reaches back to here. So the motion will be like this. You have a robot marked as red point and stylus marked as blue point. So it moves straight. Then when it rotates, the stylus will rotate like this. So it will make an angle here. This process will continue. And we have tested it for controlling the robot, this open loop control method. We tested it for controlling the robot through circular path, triangular path, rectangular path, with again stylus attached in different places like behind the robot as well as at the center of the imaginary axle connecting the wheels. When we keep the stylus at the behind the robot, you have this kind of situation where stylus take a path outside that of the actual path of the robot. And this is the simulation, and this is the actual experimental trajectory left by the robot, means stylus actually. When you have stylus placed at the center of the robot, and you have simulation here and experiment here, you can see that when stylus is kept at the center, we are going to get a much better triangle or rectangle, and you have circular path here. Again, 200 mm, this is straight by the robot. I will show the experiment conducted for circular path. So here I am giving an input of 100 as the radius, and at a 12 angular velocity, I am making the robot. So you can see the robot is making a circle. So by moving individual wheel, by changing the individual wheel velocities, you can control the path taken by the robot. In this case, it is again you can find out it's actually 200 mm, diameter is 200 mm. So that was about the open loop control. Now coming to the closed loop control, you have a classical control approach where input is given to the controller. This input is the reference path which has to be tracked by the robot. And this reference path again will be selected based on the current position of the robot and the available path. So you have some kind of reference point actually coming out of this particular module itself, the path as a whole. Then this reference position, which will be changed, varied as it moves on, and then this will be compared with the current position of the robot, and posture error will be produced. This posture error will be given to the controller, and again to the controller, reference velocity defined by the user will also be given. And these are then used to generate a control velocity, which is given to the motors of the robot and for motor control. And then from this, again the posture, new posture of the robot will be estimated using some kind of method like odometry or any other methods like image processing. And then this posture will be fed back to the power estimation level. And this is the classical control approach. For this controller, you can use a classical controller which is given by this particular equation. Again, it is it is this equation relates the linear and angular velocity of the robot with the posture errors xci, xie, theta ie, yie, and user-defined reference velocity vri and omega ri. Here k1, k2, k3 are the constants. Then instead of that standard controller, a classical controller can have an ANN phased for controlling the robot. Again, ANN, in case of ANN, you train the ANN for controlling the robot. Initially, there will be a training set, and then you train the data, the robot, and then use that for actually controlling the robot. I'll show you an example of controlling the robot through path planner generated trajectory using a standard control equation. So you have this configuration space where the robot is kept and obstacles are placed over the path, and you have a destination over here. Robot has to move from here to here. This is the actual configuration space. And then this is represented in a digital way, and then a probabilistic roadmap-based method is used to find the suitable path from the starting point to the destination point. Again, these obstacles are a little bit large because we have to consider the size of the robot while making this decision. So it's just we uh, increase the size of the obstacle for that purpose. And this is the actual path to be tracked by the robot, which is planned by the probabilistic roadmap method. Then this is a scenario where you have a robot here, you have to go to the destination point and obstacles placed over here, over these positions. And this is a video from the overhead camera. You can see the robot starting from here, then moving along the planned path. And going to the destination point. Again, that classical control approach was used here for controlling the robot. There is some error. This is because of the odometry error for estimating the position of the robot. And this estimate of the odometry is given us the feedback. Because of that problem, it's having some small error here. And again, coming to the obstacle avoidance, this new method developed from the standard bug method for avoiding the obstacle. In this case, multi-robot obstacle avoidance is possible. But we have two robots which has to go to the destination point. Both robots will move first towards the destination or goal point. Then once they detect an obstacle, one robot will circumnavigate the obstacle in clockwise direction and the other in anti-clockwise direction. And eventually they will meet at meeting point M. While circumnavigating, it will find out each of the robot will find out which is the shortest distance and which point is having this shortest distance. Once they meet, they will share this information and find out which is the actual shortest distance point out of the 2 points shared by the two robots. Then this robot will move back to the shortest distance point from there to the goal point. I'll show an animation of the same. You have two robots here, which is going to the destination point over here. And once it detects obstacle, both will move. case of Bhagwan algorithm, only one robot will move. And here this meet at this point and come back to here. In case of Bhagwan, take full circle up to here, then come back, then move. So this new method will do the object avoidance in much faster way and an efficient way. Now, I talked about the classical control approach as well as learning-based control approach. There can be other control approach as well, like reinforcement learning can be utilized for control. It's the idea of having a robot learn by itself how to accomplish a task. So RL method, I'll show you an example of RL method. So here the robot has to move from the starting point through a corridor, and it has to move in such a way that it won't hit the walls. So in this case, the robot will be trained over each iteration how to do this task. So it will learn by itself actually. So as the iteration increases, it automatically learns and completes the task. So it doesn't require any expert knowledge and are unsupervised. It's scalable, knowledge transferable, and learn while working with the environment. That is the advantage of reinforcement learning. You don't need to find out a control strategy. You can just give these are the some condition and then ask the robot to learn by itself. Here, the simulation is used first to train the robot, and then this will be again used in field in real operations. Let me show a video of using RL for controlling this helicopter-like robot. So in each trial, it is going to fail and it learns, and as the iterations increases, it automatically improves and at last it will stabilize itself. Uh, so this is RL method used for controlling helicopter-like robot in drone. And this is a framework of RL system. You have an agent which is which has to take the control action. Then this will take an action, and this action is going to affect the environment in which it operates. And this will create a new state and a reward to the agent. Based on the new state and the reward it gets, it will understand whether the decision taken was favorable or non-favorable. And based on this, agent will learn by itself and improve itself to make a good action. And this, when carried out over many iterations, eventually make the agent learn how to do the task in an efficient way. Now we use it for goal seeking as well as obstacle avoidance. This is a simulation where we gave this robot a problem like seek a goal at 500, 500. Again, this robot was not informed what it should do. We have informed the robot that it has to go to 500, 500. It is learning by itself that when it reaches 500, 500, it's going to get a big reward. So this way it's getting trained. As the iteration increases, you can find it's trying many ways to get maximum reward. So the objective of reinforcement learning, the agent is always maximize the reward. Then again, we use it for in a scenario where we need to avoid obstacle as well as see the goal. This is the graph showing the motion of the robot. So first robot will be trained, then it will be utilized for action control. So after training for 100 iterations or something, we use it for controlling the robot. You can see the robot. These are various instances. Each node, each point in blue color represent a particular scene, uh, time at which the robot has moved through this point. So this is the path taken by the robot. So you can actually should go through this way. This is the shortest path, but we did iteration. The minimum number of iterations. That's why it's taking a larger path. If you increase the number of iterations and put a better control strategy or give much more number of states, it's going to optimize the path in this way. So for now coming to the last part of the session, let me introduce some of the mobile robots which can be used in your college for research as well as hobby purposes. We have tabletop robots like Elisa, EPUB, Kilobot, etc. Then robots which can be used for indoor environments like Capera or Summit or Pioneer. This Summit can be used in outdoor environment as well. When you have collaborative mobile robots like KUKA KMB200 used for industrial purposes, Scout robot from Pharmatics, which is again an industrial robot, which is used in IC manufacturing for transferring silicon wafers. Then RB2 based on robotic and RB1 based for robotic. This RB1 base is basically a research platform. Can be used for other purposes also. Basically, it is a research platform. Then you have collaborative manipulators like Kuka LBR, M1 from Robot, Innova, and EVA from Automata. This is a cheap robot. And again, along with this collaborative mobile robots, you require collaborative manipulators for manipulating the object. Robots, collaborative mobile robots are uh, used for transferring these arms to the particular location where the manipulation has to happen. Now, before ending this slide, let me acknowledge these are the people who is behind some of the topics which I presented here. Dr. Somashegura Sirema, who is my research guide, and these are my research students like Jennifer Jacob, Joy, and Jesse. Well, thank you all, and you can ask any queries if you have. Then again, I am going to play this video from Fraunhofer, and let me ask this question to you: what are the techniques involved uh, to make this robot autonomous? So I think with this PPT, you might have understood certain techniques which can make this happen. Thank you all. Thank you all for inviting me for this seminar.
Thank you so much, sir. So now we are having a question and answer session. So I request all the participants to either post their questions in the chat box or to unmute their mics and ask. Sir, we actually had a question during the session. It was by Navya
Okay,
Thomas.
okay.
Sir, can you?
One minute. Let me see what is that. Could you? No, now, yeah, okay. Are these algorithms are these algorithms applicable for both static and dynamic environment? I think I have answered this after that particular slide. For dynamic environment, there are collision avoidance algorithms.
Thank you, sir. I hope we can wait for 2 more minutes to see whether
Okay, sure.
any questions or doubts are there.
Okay,
I
okay.
request all the participants to post their questions either in the chat box or to unmute and ask. Sir, we are having a question in the chat box.
Okay, so what will be the accuracy of the genetic algorithm compared to the other algorithms in pipeline? This I cannot answer for this because the accuracy depends on many other parameters, and uh, people are using these methods case by case, not like for accuracy purposes. Uh, for getting a higher accuracy, what they suggest is use one algorithm for the initial part, and for class final positioning, you should use some other algorithm. So won't be purely accuracy cannot be improved purely on a particular algorithm. So I don't have any answer for this particular question because there is no actual answer for this.
Sir, we have another question in the chat box.
Okay. So how effectively industrial robots can be used for various applications without human interaction? Uh, Nowadays, in industry, robots are used in most of the industries, but the problem here is there are many other things. When you use robots, you shouldn't reduce the uh, opportunity for employment. So it has to be in such a way that both should balance. Again, for pandemic situation, you cannot suddenly implement a robot. It will take some time to validate tests and other things. So it has to go. I mean, like you cannot instantaneously do it. It will take some time. You have to validate everything. Even collaborative robots, which can be used along with humans, are used nowadays in industry for solving many of the problems. Again, it is going to take at least 2 to 3 years for uh, these kind of actual robots in an industry in all fields. In some particular cases, it's only robots are applied, like spray painting in automotive industry. Most of the processes are done by robot. Again, welding. Most of these processes are done by the robots because these are less job for human and it also affect the health of the human being. So these processes are automated using robots. Using Josie Marin has asked techniques of using artificial intelligence in robots. Um, Josie, I think I have explained reinforcement learning is a kind of artificial intelligence technique and it's used in the robot. There are other artificial intelligence algorithms, machine learning or deep learning or other methods being applied in the robots. Uh, if you have asked this question with an aim to uh, with an intention like pure artificial intelligence, no, it has not yet achieved. So it will take another 50 years. It is expected that at least 50 years will take to achieve an intelligence level of human. Uh, Again, research is going in that field. So we cannot expect a robot which has the intelligence of a human being in the market within 50 years. Yeah.
Sir, we
No, next question is all the automated machines used in manufacturing sector in industry are robots? No, not actually. This production curve is there. Where in places where flexible automation is required, there robots are suitable. In places where it has to assist a human, robots are much more suitable. In places you need a mass production, you need to go for normal automation, industrial automation. Robots cannot be used in such situations because this rate at which robot will do the task is although greater than that of human, it is much more less than the automation side. So you have to compensate for that. If it is a flexible kind of automation, robots are less suitable.
Thank you so much, sir. I guess we have come to an end to the question and answer session. So now I'm glad to take this opportunity to convey my vote of thanks, especially to Dr. Robbins Mathew for delivering such a great session. And I would like to extend my warm thanks to our principal, Dr. Burshit Bibi ma'am, teachers, and all other participants for spending your valuable time with us. And now I would like to thank Dr. Robin Matthews, sir, once again for giving us such a great session and imparting your knowledge to us, sir. Thank you so much, sir.
Thank you all, and I especially thank Simi for interacting with me and making this happen. Okay, thank you all.
Now, I have a request to all the participants to remind you all to fill the quiz session, which the forms are being given in the chat box, and the link would be disabled by within the 30 minutes of activation. So, I would like all the participants to fill the quiz. So, your attendance would be marked based on this quiz session. So, hope to see you all in the upcoming sessions. We will be back with another exciting session after a break. The link for the upcoming sessions would be shared in our WhatsApp group. Thank you all.